In part 2 of lecture 4, we will answer the question, what is a context-free grammar? Like any other grammar, a context-free grammar is defined by a for tuple where G equals T, N, S, and P. T is the set of terminals, for example, the tokens that are returned by the scanner. N is the set of non-terminals, aggregates that denote structures such as declaration section, function, or expression. S is the start symbol, a non-terminal from the set of non-terminals that describes the whole thing that we are parsing. In most cases, that will be our program. And P is a set of productions, a set of rules governing how tokens are arranged to form syntactic units that make up our program. Context-free grammars are well suited to programming languages because they restrict the manner in which a programming construct can be used and thus simplify the process of analyzing its use in a program. They are called context-free because the manner in which we parse any non-terminal is independent of the other symbols surrounding it. That is, parsing is done without respect to the context in which it appears. The grammars of most programming languages are explicitly context-free, although a few have one or two context-sensitive elements. Syntax refers to the features of sentence structure as they appear in languages. Semantics, on the other hand, refers to the meaning of such structures. The parser will analyze the syntax of a program, not its semantics. So, for example, the parser will not do type checking. Semantic actions will frequently be associated with specific productions, but are not actually part of the parser. BNF, or Backus-Naur form, is a metalanguage used for describing a context-free grammar. The symbol : equals, or arrow pointing to the right, is used for may derive. The symbol vertical line separates alternative strings on the right-hand side. Here we see a simple example of an expression grammar. E, or expression, derives E plus T, or term, or it will derive simply term. Term derives T times F, which is a factor, or simply a factor. F derives identifier, or constant, or an expression inside parentheses. EBNF, or extended Backus-Naur form, adds a few additional metasymbols whose main advantage is replacing recursion with iteration. An A inside curly braces means that the A is going to occur 0 or more times. That same A in square brackets means that A appears once or not at all. So we can rewrite our expression grammar. E derives T, and in curly braces plus T. T derives F, and in curly braces times EF. E derives identifier, or constant, or E inside parentheses. This slide shows a simple grammar. The start symbol S derives capital A, capital B, little c. Capital A derives little a, capital A, or little b. Capital B derives capital A, little b, or little a. The strings that you see here can all be generated by this grammar. Can you determine how we do that? We'll begin with S derives capital A, capital B, little c. We can now expand this using capital A derives little a, capital A to get little a, capital B, little c. By applying capital A derives little b, we can now get little a, little b, capital B, little c. Now we will apply capital B derives capital A, little b to get little a, little b, capital A, little b, little c. And lastly, we'll get little a, little b, little b, little b, little c by applying capital A derives little b. In this derivation, we will start again with capital S derives capital A, capital B, little c. We will apply the production capital A derives little a, capital A 3 times. In the fourth one from the top one, we now apply the production capital A derives little b, and we get little a, little a, little a, little b, capital B, little c. We now finish by applying capital B derives little a, and we now have our string A, A, B, A, C. Here we have another simple grammar, and I think we could say this is probably a little simpler than the one we had before. S derives A, or, open parenthesis, B, S, S, close parenthesis. And we can derive each one of the 3 strings you see below. We start out with S, and applying the second of our 2 right sentential forms, we derive from it open parenthesis, B, S, S, close parenthesis. We then apply to the S inside, the first one, S derives A, and we now have open parenthesis, B, A, S, close parenthesis. We'll apply S derives A again, and we now have in parentheses B, A, A. Now we'll do it again, and again we'll start off with S derives open parenthesis B, S, S, and now we will apply the same production to the first of the 2 S's in the parentheses. And now we'll have open parenthesis B, open parenthesis BSS, close parenthesis, S, close parenthesis. Now apply again, B derives A, and we now have open parenthesis B, open parenthesis BAS, close parenthesis, S, close parenthesis. We'll then apply it to the second S in the inside parentheses, and then after that we'll apply it to the S at the end of the expression before the final close parenthesis. In the last example, we're simply going to apply S derives A. And although this may not seem like very much, it goes to show you the range of different strings we can derive simply from a relatively simple grammar. If you're interested, there should be other videos available where I actually work these out in pen and paper. Sometimes nothing can really be something very important. In writing numbers, we know how important 0 can be, despite the fact that it really means nothing. In productions within a grammar, we can have the lowercase Greek letter epsilon indicating the empty string. A derives B would be equivalent to writing A derives B epsilon. It is also possible to write the production A derives epsilon. Productions like this become particularly useful when we are preparing to do top-down parsing. A derivation is a series of replacements where the non-terminal on the left of a production is replaced by a string of symbols from the right-hand side of a production. This may be done in one step or in many steps, as we have seen previously. For example, for the grammar, S derives capital A, little a, and capital A derives capital A, little b, or c. S will derive capital A, little a. That in turn will derive capital A, little b, little a. That in turn will derive capital A, little b, little b, little a. And from that we can derive little c, little b, little b, little a. CBBA can be said to be ultimately derived from S. There are several different notations that we can use to indicate what occurs. In the first case, A with the double arrow and the alpha afterwards indicate that A derives alpha in a single step. If I write the same thing with an asterisk after the double arrow, it tells me that A derives alpha in 0 or more steps. If I have a dagger in its place, as you see here, that tells me that A derives alpha in 1 or more steps. So in the example we had earlier, we would write, as you see here, S double arrow asterisk CBBA to indicate that S derives CBBA in 0 or more steps. If the start symbol S derives a string beta, which contains non-terminals, beta is a sentential form. If, on the other hand, S derives a string beta in which there are only terminals, in that case, beta is a sentence.